So the question asks about a large box which has mass m, and it's basically moving in this horizontal plane on a flat surface at this speed v. And there's a small box on top of it, and it's moving along with the big box. Now there's a certain friction value, the coefficient of friction between the two boxes, and the question wants us to find an expression for the amount of distance that this large box here would have to stop so that this small box will not fly off the box and static friction will keep it basically glued to the box. So here I have a free body diagram for this small box, which we're looking at, and there is the normal force and there is the gravitational force. As you see here, both forces are going to be equal in magnitude, but opposite in direction. And the friction force here is going to be basically against the way that this big box is moving, because it's slowing down. Acceleration is happening this way in the negative direction. So some of the learning objectives that we want to get from this is that the idea of free body diagrams, which we can model forces with, like this one I drew here. Another big idea, is friction, which is a very important force that we have to deal with in the situation. Um, and this is another common idea of two block systems, how two weights kind of interact in this way, how the friction causes them to interact. And finally, Newton's second law, which is force equals mass times acceleration. So now we should solve the problem. So one of the big ideas and strategies that we should use to solve the problem is to connect kinematics and dynamics together. And the other strategy is to sum the forces. So using Newton's second law, force equals mass times acceleration, and we know that in the y direction, the normal force is equal to mg. So the net force in the y direction is nothing really. However, there is a net force in the x direction that basically causes the mini box on top to slow down. So we know that the only force acting right now on that box in the x direction is the frictional force, because air resistance is negligible in this question. So doing a little bit of algebraic manipulation with g being negative in the negative direction, we cross out the m's because there's masses on both sides, and we get the acceleration value to be g coefficient of friction, static friction, equals the acceleration that the block can basically have without falling off. So doing this, we are able to plug it into kinematics equations and connect the two kind of ideas together. And using this equation here, Vf squared equals Vi squared plus 2AD, we can say that the block will eventually stop and basically solve for this distance minimum or displacement minimum. So this equates out to be velocity initial squared over 2g mu static. So some common mistakes regarding this problem would be, for example, not correctly summing forces. You might not realize that the only force in the horizontal direction is friction. That's what's causing the acceleration in this case. And this connects to the idea that in this case, static friction actually causes acceleration. It's the net force, which is also very, very strange to think about, because usually static friction does not cause an acceleration, but rather stops it. So those are two common mistakes that hopefully we can avoid.